We will continue our study of optimization problems looking at a few other types. The next type we're going to look at are ones involving volume and surface area. So if we take a look at this question, we have 200 centimeters squared of material, which is available to make a box that has a square base. So that's important, square base, and an open top, so there's no lid. And we're asked to find the largest possible volume of the box and what dimensions maximize the volume. So we're asked for two things, the dimensions of the box and the maximum volume that we can make if we have 200 centimeters squared of material. So 200 centimeters squared of material really refer to the surface area of the box. And if we were to draw in sides we don't see, again they tell me that this has a square base and there's some height to it. So again, let x equal the width and the length, and h is the height. And we're told we have 200 centimeters squared of material. Well, we have a bottom to this box, and the area of the bottom would be x squared. We have 4 walls, and each wall would be x times h for the area, so we have 4x h's, and that equals 200, because that's the surface area. So there's my first equation. To find we're asked to find the maximum volume, so the volume of this box is length times width times height. X times x is x squared times h. And this is the one I want to maximize, and again, this is the one I want to take the derivative of. Again, I want to get rid of one of my variables, and the easiest one to get rid of is h, so I'm going to isolate h in this equation. So if I do that, I'm going to subtract the x squared to the other side, so I get 4xh is 200 minus x squared, and then I'm going to divide both sides by 4x, and h is going to be 200 minus x squared over 4x. The next step, I'm going to substitute that in place of h here. So my volume now is going to equal x squared, and in place of h, I'm putting in 200 minus x squared over 4x. Well, we can simplify this a little bit before we take the derivative. This x can eliminate one of those. Now I can distribute the x to the numerator to get 200x minus x cubed over 4. And if you want, you could divide each of these by 4 to get 50x minus 1/4 x cubed, and there's your volume formula. Now, like we did before, we take the derivative, so this is going to be 50 minus 3/4 x squared. We'll figure out now what makes the volume 0. So we'll add the 3/4 x squared to the other side, multiply both sides by 4, divide by 3, and I get 200 over 3 is equal to x squared. And now when I square root, I'm going to get plus or minus. Well, if I square root 203, or 200 divided by 3, sorry, I get plus or minus 8.16 is equal to x, and because x is representing a width and a length, I can only deal with the positive one. Okay, so I found x, and now I have to do my proof to make sure that it is a maximum. So I'm going to use the second derivative test, and the second derivative is going to be the derivative of 50 is 0. 3/4 x squared would be negative 6 over 4x. And if I plug 8.16 into x and I multiply, I really don't care what the number is. I know it's going to be negative because I have a negative times a positive. That means my graph is concave down at that critical number, and if it's a critical number and the derivative is 0, it has to be a max. So we know we have a max when x is equal to 8.16. So now let's go back and see what else we have to find. We have to find the height. Well, to figure out the height, I can plug right into here. So it's going to be 200 minus 8.16 squared over 4 times 8.16. So the numerator works out to be 133 divided by 4 times 8.16, and this works out to be 4.08. So I know my dimensions of the box, and the last thing I need to do is find the volume. So let's go to a new page here. To find the volume, I'm going to use formula x squared h. So the length was 8.16, the height was 4.08. So if I do the calculation here, my volume works out to be 271.67. Now my final statement, I'll include all my units. So we would say the dimensions to maximize the volume are 8.16 centimeters by 8.16 centimeters by 4.08 centimeters, and the max volume is 271.67 centimeters cubed. And that's the end of the problem. So again, very similar to how we did the other ones. Develop two equations, plug one into the other, take the derivative, solve for x, and then answer the question. Okay, the next type are poster problems. And we have a poster, and it has a margin, and most of the posters that you looked at are professionally done will have a margin, and it says that there's a margin of 6 centimeters on the top and bottom, and a margin of 4 centimeters on the side. Again, this is not drawn to scale, but so this margin up here is 6. So is this one. Whoa, it's 6. This is all side is 4, and this side is 4. It tells us the printed area of the poster, and the printed area would be the blue part, is 384, and we want to find the dimensions of the entire poster with the smallest area. Okay, so first of all, we know the area of the printed part. It's the blue part. So I'm going to use W and L for the area of the quantity we know, and it's the printed part. So I'm going to let W equal the width of the printed part, or of the print, and L equal the length of the print. So we know that the area of the blue part is 384, so 384 is going to be W times L. So there's my first equation. Now, I want to come up with a formula for the area of the entire poster, because that's what I want to try to minimize. So if I look at the area of the entire poster, if this is the width right here, and I have 4 on this side and 4 on this side, then this entire width of the poster is going to be the W, which is the printed part, plus 8, because I have 4 on each side. Similarly, the length of the entire poster is going to be the length of the printed part, plus a margin of 6 and another 6, so it's going to be L plus 12. So now to find the area of the entire poster, it's W plus 8 times L plus 12. I can distribute here and get WL plus 12W plus 8L plus 96. I can simplify this a bit more before I take the derivative. In place of WL, if I'm up here, I know that this is 384. Plus 12W plus 8L plus 96. And if I collect like terms, I get 480 plus 12W plus 8L. And this is the one that I want to take the derivative of. But again, the problem, I have two variables, so I'm going to use my first equation to isolate one of my variables. Just get a new page here. So if I go 384 divided by L is going to equal W. And now I am going to substitute that into my my area equation. So area is going to equal 480 plus 12W. In place of W, I'm putting 384 over L plus 8L. So now I have this in terms of one variable. You also could have isolated L, and doesn't really matter. You can do it either way. So 480, if I go 12 times 384, that's 4,608, and I'll move the L up to the top, so that becomes L to the minus 1 and 8L. Now I have it in a derivative-friendly form, so the derivative of 480 is 0. This will be negative 4608. So again, the derivative is going to equal, this is 480. That's 0. This would be negative 4608 L to the minus 2 plus 8, which is really negative 4608 over L squared plus 8. So there's my derivative. So I'm going to figure out what makes my derivative equal 0. It's undefined when L is 0, but you can't have a 0 length, so I don't have to worry about that one. So I'm going to set this whole thing to 0. Add this over to the other side. Multiply both sides by L squared. Now I can divide 4608 divided by 8. That's 576 is L squared. And if you square root that answer, you're going to get plus or minus 24 is equal to L. And again, because we're dealing with the length, I can only have a positive length. So now I need to prove that this is a minimum area, because they want the area of the entire poster to be a minimum. So I'm going to take the second derivative, and I'm going to go from here. So the negative 2 comes out front, and 4608 times 2, that's going to be positive 912, or 9216, sorry. And the derivative, and that would be L to the minus 3, and the derivative of 8 is 0. So I'm going to rewrite this as 9216 over L cubed. And now the second derivative test, if I evaluate my critical number of 24 into the second derivative, this is going to be positive, which means my graph is concave up, and my critical number is at the bottom, so therefore I get a minimum when L equals 24. So now I can figure out the W. So W is going to be right here. W is going to be 384 divided by 24. And that works out to be 16. So I know that the width of the printed part is 16 and the length of the printed part is 24, but we want the dimensions of the entire poster. So to finish this off, the width of the entire poster is going to be W plus 8. So 16 plus 8, whoops, is going to be 24. And the width or the length of the entire poster, whoops, to find the length of the entire poster, it's going to be L plus 12, which is going to be 24 plus 12, which is going to be 36. So therefore, I can write my final statement. The dimensions of the entire poster are 24 centimeters by 36 centimeters. Okay, you can see in all the examples we've done so far that the same procedure. We find two equations, we sub one into the other, take the derivative, and then find the critical numbers and solve the question to meet the desired answer that's being asked. This last question that we're going to look at, these ones only require one formula, and you'll notice them quite easily when you see the wording of the question. So we have a box is to be made from a square piece of cardboard by cutting squares out of each corner and turning the sides up to form walls. Given the cardboard is 40 by 40, find the dimensions of the box that will maximize the volume. All right, what's going on here? Well, we're going to cut a square out of each corner of this box. And we are going to, each of these are going to have a length x. So when we're done cutting out the corners, it's going to look like a big fat plus sign. And then we are basically folding these sides up. And when we do that, we will get a box that will be a three-dimensional box that will look something like this. Now, we can label some sides for this. So again, I'm going to let x equal the length of the cut. So if this whole side was 40 to begin with and I cut an x on each side, this length of the box is going to be 40 minus 2x, and the width is also going to be 40 minus 2x. Now, if this length of the cut is x, when I fold it up, the height will actually be x. So now, to find the volume, it's simply going to be length times width times height. So 40 minus 2x squared, because there's two of those, times the height of x. So there's my volume formula, and I only need one equation here because all my variables are in terms of x. So let's expand this. If I expand this quadratic by foiling it out, I'm going to get 1600 minus, it's going to be 160x, plus 4x squared, and I'm still multiplying this by x, so my volume, if I substitute the x in, or distribute the x in, is going to be 4x cubed minus 160x squared plus 1600x. So now if I take the derivative, I get 12x squared minus 320x plus 1600. And now we have to solve this. You could factor out a 12 to make your, I think you can take out a 12. No, you can't take out a 12 because 12 does not go in. You can only take out a 4, I believe. So if I take a 4 out, I'll get 3x squared minus 80x plus 400. And you can solve this by factoring or using the quadratic formula. And I'm going to do the quadratic formula. I'll let you work that out on your own. I think you know how to do the quadratic formula. I am just going to use my program to figure that out. And if I figure out two possible answers, I get x can either be 20 or x could be 20 over 3. So those are the two answers. Now you might be fooled to thinking because these are both positive, they're both acceptable. But if you look back at the question, x is the length of the cut. Well, if I have 40 to start with and I cut 20 off of each side, I'm not going to have a side left. So this guy is too big. Whoops. This guy is too big. So now all I need to do is figure out or prove that x equaling 20 over 3 is a maximum. So I have to do my proof. So I'm going to do my second derivative. And that would be 24x minus 320. Plug the critical number of 20 over 3 in, minus 320. And 24 times 20 divided by 3 is 160 minus 320. This is going to be negative. Therefore, my graph's concave down, which means x equaling 20 over 3 is a maximum. And they want us to find the dimensions of the box. So we know what the height is. The height is 20 over 3. To figure out the width and the length, they're the same. It's 40 minus 2x. So 40 minus 2 times 20 over 3, which is going to be 26.67. Just double checking that. Yes. So therefore, the dimensions in my final statement, the dimensions are 26.67 centimeters by 26.67 centimeters by 20 divided by 3, or yeah, 20 divided by 3, convert that as 6.67 centimeters. And that would be your final answer. All right. So there are your questions to try from page 279. And if you have any questions, feel free to send me an email. And that concludes maximization problems.